The safety and health monitoring is a very important function of our BMS in PHEV systems. Well, for example, the discharge limit is determined by the lowest cell, where the charge limit is determined by the highest cell if the balancing system is not in place. The temperature is another factor that affects the whole operation system and affects the decision process. SOC, voltage, temperature, and they are all working together to determine the available capacity. On the diagram shown here is a converted Chrysler S-Bahn PHEV just for evaluation and testing purpose. There are a number of other special control issues in PHEV power systems. Power management is a critical issue for PHEV optimization, because with optimization, with good power management and vehicle control, you can maximize the electric energy use in different driving profiles. For example, a PHEV 30 serves very well for somebody who drives 30 miles on daily commuting. But how about somebody who drives 20 miles daily? That PHEV 30 apparently has 10 miles electrical energy that he does not use on a daily basis. So the vehicle should be redesigned to fit his needs. Similarly, if somebody who drives 40 miles on a daily commuting, he needs 10 more miles. On a REEV basis, you can easily design the battery pack in different sizes, 10, 20, 30, 40, or 50 to satisfy different customer needs. But on blended PHEV, it is very hard to do because the equivalent electrical driving range is not realized in the first 20, 30, or 40 miles. It is realized in maybe combined or blended operation conditions. So for a blended PHEV, again, look at PHEV 20. What it means that is this vehicle has an equivalent 20 miles electrical range. That's what PHEV 20 means. However, that 20 miles electrical range cannot be realized in the first 20 miles. You probably can realize that in the first 40 miles driving range, or 50 miles driving range, or 30 miles driving range. Therefore, it will really depend on the driving profile of that driver, how this system needs to be designed. We discussed already in the earlier lectures that you could design a 150-mile MPG car, but if that MPG only lasts for 5 or 10 miles, that does not help very much to displace fuel usage. On the other hand, if you design a 30 MPG car that can be driven 100 miles on that MPG and then it drop, that may also make any sense for somebody if he only drives 40 or 50 miles on a daily commuting. So there's a lot of factors need to be considered in that design process, and the basic optimization can be done in a different way. A second special subject in the PHEV is a V2G concept. A V2G, we talked many times already. What it is, it's an interface between a power grid and the vehicle, and it enables bidirectional energy flow. At the meantime, you may also have a bidirectional energy flow, where you will have a smart charging system on the car to communicate with the utility company, either through the power lines or through wireless communications. And that will provide opportunities to do timely charge, to do price differentiated charging for the vehicle, and possibly using your vehicle to offset the power grid power demand, and to provide frequency regulation, voltage regulation, and stability control for the power grid. So there's a lot of good things can be done with a V2G concept. In order to do that V2G concept, we have to make sure that what is the input. If you're connecting at 110, 15 amps, you can do 1.5 kilowatts charge. For a 12 kilowatt hour pack, you need roughly 8 hours of charging time. Would that be enough? If somebody starts at midnight and his car is not charged by 6 a.m., so that may not work for many people. Therefore, you may have to build a dedicated charging port, say 110 volts, 50 amps, and then you can charge at 5 kilowatts for again 12 kilowatt hour pack. It only takes 2.5 hours for charging time. Alternatively, you may be able to build a 220 volts outlet at 30 amps, and you can increase from 5 to 6 kilowatts. If what happens, 1 million PHEVs on the road, if they are all plugged in at the same time or around the same time, you are creating a huge inrush. If every vehicle is charging at 6 kilowatts, you are at 6,000 megawatts. 6,000 megawatts. That's huge power inrush. So you really don't want that to happen at everybody charging exactly at the middle night. So the smart charging device would put some vehicles in earlier than others. And with all this 6,000 megawatts power, you're going to need 3 power plants, 3 new power plants, if they are added to the current capacity. Now, if you're taking advantage of the middle night off-peak, that's why you don't need to build new plants. If we look further, if we have 25% penetration of PHEV, in the US, we have 240 million cars on the road, 240. 25% will equal to 60 million cars. If we have 25% penetration, like what the president wanted to happen in a number of years, we are going to need 160 new power plants. That's what we're going to need. The current off-peak capacity will not be sufficient. So that's something the nation has to deal with in the long run. In the vehicle-to-grid, as we said, charging after 10 p.m. At a low level, there's no problem. You don't need additional power generation. But at a high charging rate, 8 additional power plants will be needed for 1 million vehicles if you charge at 6 kilowatts. For smart charging, can potentially reduce the inrush current and the impact on the vehicle systems. This diagram shows where you can charge the vehicle at off-peak, and in fact, you can use the battery power during peak time to offset the grid power demand. In that case, this will be done by the utility company with a differentiated pricing. For example, they're going to charge you 3 cents at night time when you charge the car, but they're going to pay you 11 cents during the day when you provide the power to the power grid. So this something that can be done to give consumers some incentive to do that, to help the utility to stabilize their power system. In the impact, we already talked about it. So if there's no smart charging, the EV owners will go home and plug in their vehicle, they're going to charge. So everybody start to charge at 6 p.m. will have trouble. We're going to need a lot of new plants. So that's where V2G makes good sense. Google is actually also working in this area. They're writing a software using a vehicle dispatch algorithm where they can put vehicles into the grid at the different times based on priorities. So there's things can be done to mitigate the congestion due to a lot of penetration of PHEVs. On the other hand, we also have to be careful about safety and reliability of PHEV operations. In a normal operation, the charging with 1772, it's a conductive charger. The plug-in has to be done carefully. For example, minors, kids shouldn't touch that, and so on. In charger stations, how do you make sure that it is protected from rain, snow, and so on? In those days, you have to make sure it is safe. During accidents, safety has to be dealt with. The battery itself, in an OEM car, it's likely not going to be in the crash zone, so therefore the rear-end crash or head-on crash may not create an immediate, let's say, explosion for the car itself, but the high voltage system and the crash itself may form a short circuit, so the batteries also needs to be protected somehow. For example, a self-disconnect and early warning for the battery if there's any potential failure is very important for the driver to know. So this things that we need to do. So now let's move on to look at the current and planned OEM PHEVs. As you will see from the next slide, there are almost every OEM is involved in PHEV development. Now we don't have all the information of every PHEV is being developed, but even if we have, will not have enough time to cover every PHEV. So we'll pick 5 PHEVs over here to discuss their design and their operation. Again, this is one you can see that this almost involves every manufacturer of vehicles from the US to Japan to China and to Europe. First one, we look at the Toyota Prius PHEV. The Toyota Prius PHEV have 2 versions, okay? There's one right now they're working on and they claim to be released very soon. They're using the current PHEV by adding an extra nickel metal hydride battery pack, identical pack to the original pack to increase the power from 1.3 kilowatt hour to 2.5 kilowatt hour, which will give you about 5 miles of driving range. So that one, it is a plug-in when they change the vehicle control so that you can take advantage of 2 battery packs in parallel. However, it may not give you a huge advantage because it only provides you limited driving range. Toyota's target is to have 1 million hybrid manufactured and sold by themselves. And they're going to have every vehicle to be a hybrid by 2020. That's a very ambitious goal, but it is very possible by the way that they work right now. There's a second version of Toyota PHEV, Toyota Prius PHEV. So this is the one that I already discussed. It has a nickel metal hydride battery, and it provides roughly 5 to 7 miles driving range. The charging takes 1.5 to 2 hours. Toyota did some testing in Europe, and they found that 50% of efficiency improvement for field trips, for trips up to 25 kilometers. 80% of the daily trips are actually under 25 miles for their test drive in Europe. This diagram shows the distribution between fuel efficiency and the distance driven per trip. As I mentioned, there's actually another PHEV under development, which the details have not been disclosed to the public yet, but Toyota is working diligently behind the scene on their lithium-ion-based Prius PHEV. But we'll see what happens in the next year or so. They're going to come out. The second PHEV, which has been very hot in the public media, is the Chevy Volt by GM. They call this REEV or EREV. It is a range extended electrical vehicle. It is a series configuration, which means they have a motor that directly drives the vehicle, and then they have an onboard engine and a generator to develop electricity. It is a purely electrically driven system. You can see that this is the layout of the vehicle system, and the specs of the system included a 16 kilowatt hour lithium-ion battery pack. It's going to be made by CPI Compact Power Inc. With the batteries provided by LG. And GM is actually announced that they're going to build their own assembly plant to make the battery packs for themselves. The battery can provide 140 kilowatts of power at any given moment when they are fully charged. It can be recharged at 110 outlet by 6 to 6.5 hours. The motor is an induction motor that can provide 120 kilowatts of power. The continuous electric 45 kilowatts, continuous mechanical 40 kilowatts. The engine is a 3-cylinder turbocharged engine, 1 liter, 160 horsepower, 120 kilowatts. The electrical range is predicted at 40 miles. In fact, because it has a 16 kilowatt hour pack at the beginning when you buy the vehicle, it probably provide more than 40 miles range. But that 40 miles is more towards the end of the vehicle life. You can still get roughly 40 miles range. The estimated fuel economy is 50 miles per gallon during charge sustaining operation. For the first 40 miles or less, there's no MPG because it doesn't start the engine. If you go to 60 miles, combined with the first 40 miles, if you calculate the fuel consumption and total miles, you can get 150 mpg. For 80 miles, you can get 100 mpg. Acceleration is 0 to 60 miles is 8 to 8.5 seconds. Top speed 120 miles. Okay. A third PHEV is also by GM. That's a second wheel two-motor hybrid. Now this is a blended PHEV, which was supposed to come out this year, but due to the economy situation, due to the reorganization of GM, so this model is temporarily delayed, and the date that it's going to come out is unknown. But this is a blended PHEV that has a 50 kilowatts motor that can be used to drive the vehicle, and the battery packs, the size is unknown at the moment, but the idea is to give you 15 to 25 miles range based on the size of battery selected for the vehicle. But that 15 to 25 miles electrical range, again, is not realized within the first 15 to 20 miles, but it's realized within, let's say, maybe 30 to 40 or 50 miles range. Ford also developed a PHEV based on their Ford Escape Hybrid. This Ford Escape Hybrid has a motor that is 75 kilowatts. They have produced 21 of these PHEVs so far and did some fleet testing with Southern California Edison and some companies. The battery is a 10 kilowatt hour pack. It is enough for 30 miles electrical driving on this small SUV. So if you calculate the fuel economy, because also it is a blended PHEV, you are not going to get a pure electrical driving range right away. So you're going to get equivalent electrical driving range. The fuel economy can get up to 120 miles per gallon, depends on how you calculate the MPG, depends on how many miles that you're going to look at. But overall, the equivalent electrical driving range is 30 miles. Next hybrid is a Chrysler Town & Country Minivan, which is also under development by Chrysler. It is also a blended PHEV, a two-motor hybrid with a large battery pack. The powertrain is the same as the conventional HEV. It has 11 kilowatt hour battery pack. It can achieve 53 miles per gallon in its first 50 miles driving. So the equivalent miles electrical range is roughly 22 miles. The total range will be 700 miles with all the gasoline consumed. The towing capacity is going to achieve 1,000 pounds. And so far, this is only minivan PHEV being developed. Now, it's not ready yet. It's being developed. The diagram that you see, the bottom is a prototype for testing and characterization, and the top is how the vehicle appears. So those are the OEM PHEVs that I want to discuss. In addition to those, you're looking at BMW, Nissan, Honda, in China, BYD, Chery. They're all working or already have a prototype model available in the PHEV space. They are still conducting extensive testing and characterizations. So those vehicles may not be available right away to the consumer, but in the immediate future, like this year, later this year, early next year, you will expect some OEM PHEVs available, and later next year and early the year after, you will see more PHEVs available in the marketplace. But at the meantime, since there's no OEM PHEV available for consumers, there have been aftermarket PHEV conversion companies that provide PHEVs. It either help you to do the conversion or they sell you the converted PHEV from conventional EV. A number of companies are involved in this work. I'm going to introduce 5 of these companies here. One Power Solutions, Hybrids Plus, A123 High Motion, Energy CS, and and the last one is the Prius Conversion Kits that is publicly available on the internet. One Power Solution is a small company, startup company that help develop PHEVs based on current HEV. They have developed 4 different types of PHEV, including the Prius, the Chrysler S-Bahn, the Chrysler minivan, and the second wheel. And then this second wheel is not OEM second wheel PHEV, but it's converted by One Power. You can see with all the different energy rating for the battery pack, the ranges are also a little different. The Prius PHEV with a 7 kilowatt-hour pack, the equivalent range approaches roughly 30 miles. With the Chrysler S-Bahn 11 kilowatt-hour pack, equivalent E-range is roughly 21 miles. With the minivan, same battery pack, roughly 25 miles, with the second wheel working underway with a 10 kilowatt-hour pack, equivalent estimated predicted range is roughly 30 miles. Hybrids Plus is a company based on Colorado, and then they do 2 type of conversion. One is Prius, another one is the Escape. They have their own. They have their own proprietary BMS that replaces the Prius BMS and battery. They use A13 26650 lithium-ion battery, 9 kilowatt-hour. So what they do is they remove the original battery and the battery controller. They put the new battery in the system. You can see on the diagram on the right, this is the original battery pack before, in front of the spare tire. Well, Hybrids Plus has designed a L-type battery pack that will still help you to with the availability of accessing the spare tire. So the batteries, because they are cylindrical, smaller cells, they have more than 1,000 battery cells put together to form the pack. The Prius 15 and Prius 30 each provide 15 miles and 30 miles range. The total range is 25 and 50 miles range, which means within that range you're going to get a much higher MPG, up to 100 MPG. The mass, because increased battery, increase 30 to 70 kilograms, depends on which battery pack you want to replace. They have their charger, their own charger, their BMS, and their controller. So their charger would charge from 110 volts AC, 15 amps, roughly 5 to 9 hours charging. And their controller, BMS, interacts with the vehicle controller, which will replace all the battery controller CAN messages floating on the bus. However, last year there is an accident that due to some failed connection, the loose connection that caused spark and which eventually caused the fire of a Prius. So right now they no longer offer this Prius PHEV conversion. However, they are still offering the Prius, the Hybrids Plus Escape hybrid conversion. The Escape conversion can reach 25 miles equivalent electrical range. It is a blending mode up to 50 miles, which means beyond 50 miles, it will go back to normal HEV operation, normal HEV fuel economy. The energy in the battery pack is 13.3 kilowatt-hour. Additional weight is 56 kilograms. They removed the original pack and put this new pack with their own charger, their BMS, and a controller. So this is available. You can actually order online and they will do the conversion for you. The cell that they use is the same one they use in the Prius. It's a 26650 from A123. And again, it's charging from 15 volts AC input, up to 9 hours charging time. A third company that does the converging is A123 itself. There's a company called High Motion. A year ago, A123 bought High Motion, so now it's called A123 High Motion. They provide you with a 5 kilowatt hour battery pack in addition to the original batteries. Well, so what they're doing is that they're not touching the original vehicle battery and the battery controller. They're only adding this 5 kilowatt hour pack to the original battery pack, so you will have more energy available. You can order 5 kilowatts, or you can order 2 that will be 10 kilowatt hour. So this battery is a different battery. They were so-called nanophosphate lithium-ion cells, 5 kilowatts, 5.5 hour charging time. It's 180 pounds. It is in place of the spare tire. So which means when you put this in, you have to remove spare tire, and then you put this battery in, and it will give you roughly 10 miles driving range. Their suggested retail price is $10,395 plus tax with 3 years warranty on the parts. So this is how it looks when you put the batteries in the original spare tire, where the original spare tire is located. Energy CS is a company actually earlier involved in PHEV conversion. They use Valence 18650 cells, 9 kilowatt hour pack with also a certain equivalent electrical driving range for the vehicle. In order to convert a HEV to a PHEV, there are 2 methods you already look at. One is to keep the existing battery pack by adding additional battery to the original pack, so you'll have more power. The original battery and the battery controller are not touched. So the system is much safer to operate, but the problem is that you're not taking full advantage of the add-on battery pack. Another method is to replace the existing battery pack. So take out the battery, take out the controller, put a new battery, put a new controller. There's more risk in this conversion because if there's anything in the new battery controller does not match the original vehicle battery controller, you may have trouble to put the battery in a fault condition. So therefore, converging in this type needs a lot more careness. But both systems, the second converging process will give you the freedom to take advantage of the new pack. You can basically change all the information the battery controller is supposed to be, such as charge limit, discharge limit, SOC, so that the vehicle system will take advantage of it. But if you keep the existing pack, since you're not touching the battery controller, it's very difficult to manipulate information on the CAN bus. Therefore, the vehicle controller does not take a full advantage of the add-on battery pack. So to keep the existing pack, the way is to add additional battery pack. For example, in the Prius, you would put the battery pack behind the original battery pack and in place of the original spare tire. When you put this battery pack there, you have to constantly release energy from the add-on pack to the existing pack so that the vehicle will use the energy. So therefore, you may need a DC-DC converter in order to do that purpose. If you simply put the original pack and the new pack in parallel, it may not give you, again, the full advantage to realize the kind of equivalent electrical driving range. The converging of Prius HEV into a PHEV is very popular. There have been many companies doing that. Also, Hobby is doing they are doing this on their hobby. They're doing it on their own. So on the internet, you can find the converging diagram that tells you exactly what to do and how to do it. So this diagram is downloaded from internet, and you can find this by Googling Prius PHEV converging. On this diagram, there are portion of the diagram is the original OEM parts, then the other portion are replaced by the new battery system, including the battery pack or may include your new battery controller. In some other aftermarket conversion, they only replace the battery pack but don't replace the battery controller, the battery ECU. By keeping the battery ECU, the good thing is that the battery ECU will produce all the information needed for the vehicle controller, so there's no risk of not getting a car running. But the issue is, by keeping the existing battery ECU, you are not able to manipulate a lot of the information. Or even if you can, but the CAN bus will have two different information flowing around. So you will have trouble getting the system in a constant and a stable operating condition. When you remove the existing pack, the new pack and the new battery controller needs to match exactly the original battery ECU information, whether it's input or output. So all CAN messages has to be identical. Otherwise, the vehicle will enter into a fault condition. This is the terminal that connects the battery ECU to the vehicle controller. And then you can see there are 9 actually different pins that we have to identify. The CAN high, CAN low, there's a 12 volts power supply, there's a fan control, and then there's a 12 volts ready, and there's 12 volts always on. There's also ignition indication. So this information can be used by your new battery controller, and your new battery controller has to send out corresponding CAN messages to the vehicle controller, so that vehicle controller will know the vehicle condition, and then it can start it to run the vehicle. For example, this chart shows the start sequence of the Prius. When you start the vehicle, the K1 will give out a short pulse, and then it will test whether there's a short circuit. So the K1 is a relay number 1. So they're going to close relay number 1 to see whether there's any short fault in the circuit. If there's none, then they will close K3 after 235 milliseconds, and then they're going to close K2 after another short time, and then this time they're pre-charging the power electronics, because when you switch on the vehicle, the battery is at a high voltage, but the power electronics, the DC link, will have 0 or very low voltage. If you switch the battery on right away between the power electronics and the battery, you will have a very large inrush current. So the pre-charge circuit is going to have a resistor in series with the relay. So when you close the relay, the current is limited. When the DC bus voltage reaches approximately the same as the battery voltage, you close another relay, that is K2. Okay, once K2 is closed, the whole system is powered up, and then the vehicle, after another 40 microseconds, the vehicle is all good to go. If before closing any of the relays, if anything fault is happening, it will not start the vehicle. So the battery controller needs to wait for the vehicle ready, ignition ready signals before it closes any relays. So this is how it works in the startup. In shutting down the vehicle, it's just opposite procedure. For example, the vehicle ignition signal will disappear, and then the ready signal will disappear, and then the K3 will be at a lower voltage. Then you're going to you're going to open K2 at first, and then you open K3. So at that moment, the whole vehicle is shutting down. The diagram and the procedures that I described in the earlier slides are available on the website. I give here, you can basically go online and download and do the converging if you have an interest to do it on your own. Or you can ask companies to do the converging for you, and you pay a fee. The companies that are involved in this converging process are more than 10 companies. They're all listed here. So that basically covers the very basics of PHEV and HEV. There apparently a lot of contents already covered, including the components, the design, the systems, the batteries, the management system, the control, and the converging, and the OEM manufacturing for PHEV, V2G, and so on. So at this moment, I want just to continue for the next 25 minutes to discuss another topic, which is the dynamics of a power split eCVT. We touched this topic a little bit earlier, and I mentioned that time I want to discuss the details of the two-mode hybrid, how it operates at this moment. At an earlier time, when we discussed previous HEV operation, we only focused on the steady-state operation, and we even neglected all the inertia, and we neglected all the losses in the gear systems. In fact, in the planetary gear operation, each gear will have its inertia, and all the rotating components, whether it's a driving shaft, whether it's an axle, or whether it's a motor shaft, they all will have inertia. With that inertia in place, the relationship is not the kind of one that we've seen in steady state. So we just want to take a little bit look at these three different types of electrical CVT operations: the Prius, the Camry, and the two-mode hybrid, and then see how it operates. This is a simplified diagram of the Toyota Prius planetary gear system. This is the same as we discussed before, but this is a simplified drawing to calculate the dynamics. In this diagram, it is a front-wheel drive, so connected with the wheels are the final drive. You can see on the final drive, there's the final drive driving the axle, so the axle would have omega, speed, m is the J is the inertia, m is what is m, and the gear ratio between final drive and the wheels can be described as GA to R, so axle to ring gear. So final drive to ring gear is hard linked with gears. So the final drive also have omega, m, and j. The ring gear has also omega, m, and j of its own, the speed, inertia, and so on. And S sun gear, carrier, so each of them will have it. The MG will have its own set of J, M, and omega, and ICE will have its own omega, M, and J, and the motor generator 1 is the generator that also has its own. The gear ratio between each gear is named in the convention like a GR to S, means gear ratio from rain to sun. GE to S means gear ratio engine to sun. So that's how it operates. By this convention, we can write down that the final driving inertia is calculated by using the axle inertia plus the final driving shaft. The final driving shaft itself has inertia. The axle inertia is converted to final drive because it's a gear ratio. When the speed reduction, the inertia is also reduced over here. The motor shaft will have motor shaft itself. So JM is a motor shaft inertia. JMOT is the motor itself, plus the ring gear, because motor is connected to ring gear, plus final drive, because final drive is also connected to ring gear, and plus transferred from sun gear and generator. So sun gear and generator on the same shaft, they have inertia, they're transferred to the motor shaft. So the motor shaft has the final drive, has the ring gear, has its transferred sun gear and generator inertia. So you can see this is the JM. On the generator shaft, you will have the generator shaft inertia itself plus the sun gear inertia. So that's the generator shaft. On the engine shaft, you will have the cranking shaft itself, you will have the carrier, and then you will have transferred inertia from the generator shaft, because this is the planetary gear. So generator shaft inertia is also transferred to the carrier. So this is the set of inertia calculations. G is the gear ratio, and S stands for axle, C carrier, G is generator, S is sun gear, R is ring gear, MOT is motor. Once you have those gear ratios calculated, which is shown here, engine to sun is the gear ratio, GE to sun, K plus 1, and ring to sun is called minus K. And this convention is a little bit different from what we used before, but it's okay. It's just how you calculate the gear ratio. The generator speed would be engine speed plus ring gear speed. Well, because we use the gear ratio as negative. If gear ratio is positive, then the engine speed minus ring gear speed will equal to engine speed. Again, each one of them will have a gear ratio. So these gear ratios, basically, in the past, we have, let's write down this one. We said the carrier speed is ring gear speed plus sun gear speed each times a gear ratio. So in this expression, if you write down omega G, which is generator, which is a sun gear, so omega G is equal to omega S. That is going to equal to NR plus NS divided by NS times omega C minus NR divided by NS times omega R. So you can easily identify what is K. So K is equal to NR plus NS. Okay. Once you have this equation here can be written as omega G is equal to K plus 1 times omega C, which is the engine speed, plus K times omega R. So this is how we get this set of equations from the planetary gear systems. Those are the three gear ratios. Now how about the engine speed? The engine speed is coupled and it can be calculated by using this, by reversing that expression, which means it's going to be omega G divided by 1 plus K minus K divided by 1 plus K times omega R. So you can derive any speed on these three shafts. Because omega C, omega G, omega R, they are basically the same thing. By the way, omega R is same speed as omega M. So you have all these three speeds available. With all these three speeds available, you can now transfer the inertia in the system. So JGC, generator to carrier, is generator itself plus sun gear, then times those two gear ratios. So the equivalent inertia will be the JE engine plus JG prime. That's the equivalent inertia on the carrier. And the MQ is the inertia on the motor shaft, which is also connected to the final drive, and the ring gear is the motor inertia plus G squared times J prime G. So you get this set of inertia. Now you can write down the speed relationships of the system, speed and torque relationships. So if you look at the generator torque, which is going to be engine torque minus the inertias of those two systems, the omega E and omega M. So that's derivative of speed times the inertia gives you the inertia torque. The ring gear will have motor torque plus engine torque and then plus a number of inertia terms. And the road resistance is basically the street resistance plus MA. MA is acceleration. So in this case, if we write down all these equations to simplify them, you would have said that the road load can be translated by 3 resistance, ruling resistance plus aerodynamic resistance plus gravitational resistance, then plus MA. So that's the road load. That road load has to be balanced by torque on the final drive. So the final drive is TR. When you have inertia terms, all those torques are not going to be the same. But when you have entered into a steady state operation, you can eliminate all the inertia terms. Therefore, you will see that TG, generated torque, is proportional to engine torque divided by GE2S. And that's the one that we derived earlier based on the other convention that we use. You can derive the ring gear torque, which is on the final drive, ring gear. So that's motor torque plus a portion of engine torque. In this case, they used this minus sign just to get the conventions right, times GR2S divided by GE2S. So that's how you get this ring gear, which is torque. So, and again, the ring gear torque has to be same as the load torque. So this is how you calculate in the steady state. The steady state torque relationships, as I wrote over there, you already have it. So the second one is the Ford Escape and the Mercury Mariner hybrid. So the Escape and Mariner hybrid, those two hybrids are the same. They are also very similar to the Prius hybrid, with the difference that the motor is not directly connected to ring gear, but through another gear. So if you look at the diagram, the difference is really before the final drive and after the ring gear. In the Mariner, the ring gear is directly connected to N3, MG2 is connected to N1, but N2 is connected to final drive. This is a simplified gear drawing. You already saw this earlier in another part of the lecture. So the ring gear part will be eventually the same, but the inertia part, the inertia on the final drive and the ring gear part are going to be different. So this is the only place that you're going to find the difference. Therefore, the derivation will be much simpler because we don't have to worry about the other parts. So the gear ratio at final drive is going to be the 4 gears. Okay, the gear, if you look at back again, N1 between N1 and N2, between N2 and N3, okay, and then between MG2 and R1 and R and N3. So those are the relationships. The shift in inertia can be also calculated.